Analytical Chemistry 1, Lesson 40. Most of the time, a sample is titrated to determine the concentration of the acid. We do not need to measure the pH continually throughout the titration. We just need to know the equivalence point. Then, with the known titrant concentration and the volume of the aliquot, we can calculate the unknown concentration. Using a chemical indicator to find the endpoint of a titration is such an approach. An indicator is a molecule whose color is different when it is in its acidic or basic form. There are many different indicators available. Their utility spans the entire pH range from 0 to 14. Here are some examples. Methyl yellow changes from red to yellow as the pH rises. Its transition occurs under rather strong acidic conditions. Bromocresol purple changes from yellow to purple with increasing pH. Its transition is more in the middle of the pH range. Phenolphthalein is colorless as an acid but turns pink when converted to its conjugate base form. Indigo carmine changes from blue to yellow at the very high pH range. Now there are many more indicators available. As well, they can perform many functions beyond acting as pH indicators. Some are used as dyes. Many are used in microbiology to provide a pH-dependent stain for cells. Some are used in surgical procedures to detect the leakage of body fluids that indicates a change in pH. Some can be used for toys. Dolls' hair can change color. Disappearing ink can be used to send secret messages, and so on. Many of them are derived from natural sources. The molecule used in litmus paper is an indicator derived from certain lichen species. Turmeric is a spice from the ginger family that changes from yellow to brown as the solution becomes more basic. The flowering plant hydrangea will have blue leaves when grown in acidic soil and red leaves when grown in alkaline soil. Others are produced through synthetic organic chemistry techniques. Where does this color change come from? Well, they're just acid-base molecules, and the Henderson-Hasselbalch equation applies to them as well. When any acid-base molecule is present in a solution with a pH that's equal to that molecule's pKa, we know that the ratio of the conjugate base to the conjugate acid is 1:1. Their concentrations are equal. When the pH rises by 1 unit, the conjugate base form now has 10 times the concentration of the acid form. If the pH is 1 unit below pKa, the acid form has 10 times the concentration of the base form. This is the most rudimentary rule of thumb for the use of pH indicators. The change in color occurs within plus or minus 1 pH unit of the indicator molecule's pKa. Now, in practice, this is not quite the case, because the intensity of the color, which is a function of its molar absorptivity, of one of the forms is never identical to that of the other form. Each indicator has a specified range, which is commonly less than the 2 pH units suggested by our analysis above, that can be used to guide our choice of indicator. Here are the operational ranges for the example indicators that I mentioned earlier. Methyl yellow's transition is between 2.9 and 4.0 pH units. Bromocresol purple changes color between 5.2 and 6.8. Phenolphthalein has 3 transitions, but the most commonly used one is between 8.3 and 10.0 pH units. Indigo carmine changes from blue to yellow between 11.4 and 13 pH units. So how should one go about choosing an indicator in a specific situation? Well, you need to know something about your analyte sample. Perhaps you are titrating a solution known to contain 2-naphthoic acid. Its pKa is 4.16. We know that the equivalence point of a titration is where we have a solution of the weak conjugate base of the acid. We can use the tools we have developed to estimate where the equivalence point will occur, but that depends upon the formal concentration, so we need to have an idea of its concentration. Some quick arithmetic with our approximate equations, or by using Goldseek to solve the cubic, tells us that for a solution concentration around 10.2 to 10.3 molar, we can expect the equivalence point to be in the range of 7.6 to 8.1 pH units. This is what the titration curve would look like for a specific formal concentration of the acid and titrate base. Now again, if we are using an indicator, we do not know this curve, but all that we are trying to determine is the volume at the equivalence point. And in this case, the answer is 33.33 milliliters, but we do not know that yet. We just know the anticipated range of pH. And if you look at this titration carefully, you will find that at about 33.1 milliliters of titrant, before the equivalence point, the pH is about 6.30. And at about 33.7 milliliters, just after the equivalence point, the pH is 10.20. So with the addition of about 0.6 milliliters of titrant, the pH has changed by almost 4 pH units. And if we pick any number within this range for the equivalence point, our relative error is less than 2%. In many situations, that is an adequate result. So how do we choose an indicator? Anything that changes in this range would be acceptable. And we can refer to any table of indicators. You have one of these in your textbook at the end of this chapter or on titrations. Here are three possibilities. Bromothymol Blue starts its change from yellow at a pH of about 6. It's fully blue by pH 7.6. Looking for the fully developed blue color would make for a recognizable endpoint for the reaction. Phenol Red starts changing from yellow around pH equals 6.4 and is red by 8.0. This is well placed also. Finally, Thymol Blue starts to change from its acidic form of yellow at 8.0 and is blue by 9.6. Each of these indicators will provide a different color change in a slightly different pH range, but the additional added titrate volume will be very small. There are many more possible indicators that could also work, but how do you decide what color will be the endpoint? Well, note the language I've used. I've called this the endpoint rather than the equivalence point. The endpoint of a titration is what you have decided to identify. It may be, but is more likely to not be, the same as the equivalence point. The difference between the endpoint and the equivalence point is known as the titration error or the indicator error. You have tried to minimize the error by choosing the right indicator, but the color determination is still somewhat subjective and can vary from one scientist to the next. Well, two things can be done. If the 2% error is acceptable, don't worry about it. If you need more precision, calibrate your choice of endpoint color against a solution of known concentration. Determine the error, which is positive or negative, and use it to correct your unknown sample measurement. The color that will be the endpoint is for you to decide. What is important is that you choose the same color for the same indicator every time. And only use as much indicator as is required, just a few drops. The indicator is itself an acid-base molecule and will consume titrant. More than a trace will skew your results also. If calibrated, this can also be corrected. More accurate results can be obtained using a spectrophotometer rather than your eye as a detector of color change. But that is for another course.